Imagine teaching a neural network to solve physics problems, not by brute force learning, but by rewiring space itself. That's the core idea behind the Adaptive Vekua Cascade, a breakthrough in scientific AI. Standard neural networks struggle with high-frequency physics. They're biased toward low frequencies, like a microphone that only hears bass. Even advanced models like SIREN or hash grids fail under noise, sparsity, or high-dimensional chaos, like 3D turbulence. Here's the fix. Instead of forcing a network to learn physics from scratch, we let it learn the right coordinate system. A deep network warps the physical domain into a latent space, a kind of idealized lab, where the solution becomes analytically simple. Then on this warped space, we use a fixed basis of generalized analytic functions, harmonic waves scaled by magnitude like Taylor expansions for frequency. And here's the game changer. We replace the final layer with a differentiable linear solver. No more slow gradient descent. In one forward pass, we compute the optimal spectral coefficients in closed form, like snapping a puzzle into place. Backpropagation then refines the warping, not the basis. The result? 840 parameters versus 4.2 million in grid-based methods. 2-3 times faster convergence than implicit neural representations. State-of-the-art accuracy on high-frequency waves, sparse reconstructions, and 3D Navier-Stokes turbulence. This isn't just faster, it's smarter. By aligning the model's inductive bias with physics, we break the curse of dimensionality. We're not approximating smooth fields with piecewise linear grids. We're finding the coordinate system where they're harmonic. It's a fusion of deep learning and classical approximation theory, a new paradigm for memory-efficient, spectrally precise scientific machine learning. The code is open. The future of physics-informed AI. It's not just neural, it's analytic.